Optical fibres. Here we have a glass or plastic fibre, and if we send a ray of light from the end, it will travel through like this. Placing a normal, a line at 90 degrees to this face, we can label this I, the angle of incidence, R, the angle of reflection. As always, the law of reflection applies, and so angle of incidence equals angle of reflection. If the angle of incidence is greater than the critical angle, we will get total internal reflection. The fibre can be bent like this, and the signal will still totally internally reflect, allowing us to send a signal around a corner. The construction of an optical fibre is a little bit more complicated than shown on the last slide. Here we have the optical fibre and an end view. The fibre is encased in a cladding of a lower refractive index than the fibre. That means the light will travel more quickly in the cladding than it will in the fibre. There is also a plastic sheath which gives strength and protection to the fibre. Here we have two fibres that are in contact at this point to demonstrate the need for the cladding. I've coloured the fibres differently just so we can distinguish one from the other. Now if a signal was travelling along this fibre, it's possible that it would transfer into a different fibre where they're in contact. There's no change of refractive index at this point. Likewise, a signal could pass from the bottom fibre to the top. This would clearly mix up signals, which could be very dangerous in terms of security and confidentiality. The cladding ensures total internal reflection to avoid a loss of energy from the outer face of the fibre and to prevent this crossing of signals. Here is another way to reduce the effects of multi-path dispersion. We have the cladding of a lower refractive index, but now the fibre itself has a refractive index which is higher at the core than at the edges. The light will travel faster at the edges of the fibre than in the centre. Here we have an end view and a graph of refractive index as we go across the profile of the fibre. This is the fixed low refractive index of the cladding. When we're in the fibre, the refractive index rises to a peak at the centre and falls again before we get to the cladding. The ray of light will now travel through the fibre something like this. This is called a graded index fibre, and it reduces the effects of multipath dispersion. It has a maximum transmission rate of over 1 GHz over a kilometre. That means we can pass information much more quickly over a graded index fibre than a non-graded index fibre. Now to look at some of the ways that energy is lost from the signal passing through an optical fibre. Here the light is coming out. This will make up our signal. So this is the exiting ray, which will refract on exit, but a small amount of light will reflect at this point. This energy is effectively lost from our signal. Also, as the ray of light passes through the glass, a small amount of it will be absorbed by impurities in the glass. The signal gets weaker as it travels through. This is absorption of the signal. Any way in which the energy is reduced is called attenuation. The signal has been attenuated. We get round this problem by having repeaters, which will boost the signal strength as it goes along its way. This compensates for attenuation. You'll have seen this situation before, where a ray of white light enters a glass prism and is split up into the colours of the rainbow. This is called dispersion, and it occurs because different wavelengths of light travel at the same speed in a vacuum, but different speeds in different materials. So the red light has been slowed down less than the violet light, and so has been refracted by a smaller amount than the violet light. This clearly is undesirable in optical fibres, and so we must use as close as possible to monochromatic, or literally one wavelength, light. Finally, to look at some of the advantages and disadvantages of optical fibres over more traditional copper cables. Well, optical fibres can carry a higher bandwidth. We can pass more information along an optical fibre than a copper cable. They're lighter and so easier to support, and they have lower energy losses than copper cables, meaning we can send a signal for a longer distance between repeaters. Remember, they boost the signal as it passes through. They don't suffer from interference or crosstalk. They're secure from tapping. You'd need to actually break into the cable to tap the signal. With a copper cable, you can place something around the outside which senses the changing magnetic field due to the electrical current. They don't produce any sparking, so are safe in flammable explosive areas. And they have a very high resistance, so they're safe to be used near high voltages. Copper cables, on the other hand, are cheaper than optical fibres, easier to connect, can carry electrical power as well as a signal, which could be useful in some applications, but mainly they were there first. Here I've removed the cladding for clarity. This diagram shows two of the many possible routes that a ray of light could take through an optical fibre. I've used different colours here just to distinguish between the two paths. You can see that the red route is clearly significantly longer than the blue route. So if both these rays entered at the same time, the blue route would leave the fibre first. What effect does this have on our signal? Well, if we send a pulse in, something like this, and the light for the pulse takes several different routes, as shown, the information will be spread, so we'll end up with a longer and weaker pulse coming out. This effect is known as multipath dispersion. Multipath dispersion can lead to pulses merging. For example, here I have two separate pulses. I've done them in different colours just to distinguish between the two. As the two pulses spread due to multipath dispersion, we could end up with something like this coming out. The two pulses have now merged. This effect limits the frequency of pulses we can send down a fibre. One way to improve the situation is to have a narrower fibre. This then reduces the path difference. The red path is now not quite so much longer than the blue path. With a narrow fibre we could have a maximum transmission rate of around 10 to 20 MHz over a kilometre of optical fibre. If a signal of this frequency was sent over longer than a kilometre, there would be a danger of the pulses merging.